Thank you, Laura, and thanks everybody for coming out on a night that has weather that is more appropriate for Mars, I think, than for the Earth.
We wish.
Maybe it will be. We'll find out. I wanted to give this talk. Usually the communications office has to go twisting arms to get people to give a talk, and all the people that do it give great talks, but getting someone to do it is often difficult. I wanted to do this one because this question about terraforming Mars is something that I read about in the papers very regularly these days. It's a topic that is of tremendous interest, and we're seeing more and more about human missions to Mars, about the potential for life on Mars, and I thought this would be a fun topic to let me bring all of those issues together under one umbrella. The interesting thing to me about Mars is that it's something that really draws everybody's attention. There are music groups named after Mars and record albums, if anybody remembers what those are, that include topics like life on Mars, if anybody remembers who David Bowie is. I'm sure, how many people in the room have seen the movie The Martian? Okay. Okay, let's try it the other way. Has anybody not seen the movie? There's one, two. Shame on you two. I know you two, too. This thing in the lower right, if you know what it is, I don't have to explain it to you. And if you don't, there's no way I can explain it. So I'm not even going to try. I hope everybody recognizes Elon Musk's Tesla. I don't think that's him in the suit, but he launched it on a trajectory that will cause it eventually to hit Mars. And of course, Marvin the Martian, you can't give a talk without him. The driver of this interest, I think, is the fact that Mars in our solar system is the most likely place to have life other than the Earth. I think we know about life on Earth. And it's also the place that has the best chance of us going and finding it because it's relatively easy to get there from here. Certainly easier than Europa or Enceladus in the outer solar system. So this question about life is one that really draws interest, and I think that's the driver here. I'm going to start, since everybody's seen the movie The Martian, I don't really need to dwell on some of the background, but I'm going to start there anyways. Mars is the next planet out in the solar system from the sun after the Earth. It's about half the size, half the diameter of the Earth, and it has an atmosphere about a little under 1% as thick as the Earth's atmosphere. I hope I didn't need to put the labels on them. I hope you can tell which one is Mars. Because it's farther out, because it has such a thin atmosphere, Mars is colder than the Earth. The average temperature at the surface is about 50 degrees C below the melting point of, below the freezing point of ice. It can get up to room temperature here, but only middle of the day at the equator during summer. Usually it's a lot colder. It can get really, really cold. When we look at the surface of Mars, we see a place that reflects this cold nature. These are our two pictures, one from the Viking spacecraft, which is ancient history now, 43 years ago, and one from Curiosity, which is still operating on the surface. We can look at the geology and talk about what processes are going on, but we're looking at a very cold, dry planet. There's very little, if any, water. For those of you that know better, and I know there are a couple, I have to put a little asterisk and say there's really some water, but not that we would want to talk about. So if you push me on it, I'll tell you why. Please don't, because we'll be here for an hour talking about perchlorates and processes that you don't want to know about. The temperatures are cold, the atmosphere is dry. We have essentially no water to speak of. Despite that, we have evidence that there may have been recent water. We're looking at the side of a scarp here, a feature that's very common, what looks like a gully that's been carved by water. These are small-scale features, so it must have happened very recently, within the past, say, million years. And we see other features. In this time series, you can see something darker flowing downhill. And the suggestion has been made that this is due to flow lubricated by water. Both of these are very controversial, and people are very clever at coming up with good alternatives involving dry avalanches and other processes that don't involve water. Despite that, we see a lot of evidence for water in the Martian environment. We'll start with the polar caps. This is about 600 kilometers across. What is that, 400 miles across? This is the North Polar Cap seen in the summer. All the white-ish stuff is water ice. All the reddish stuff is dirt. When you look closer up, these dark lanes show what look like alternating layers of water ice and dust, or layers of water and dust mixed in different proportion. Clearly there's a lot of water. If you took all this and spread it globally, it would be a layer maybe 10 meters thick, 10, 20 meters thick. That's a fair amount of water. So we know there's a lot of water on the planet, and we know that in ancient times there's been liquid water. This is one of my favorite images. It's from a surface that's very heavily cratered, which means it dates back to between 3.5 and 4 billion years ago when it formed. And we see these branching valley networks that look like they were carved by water. The fact that these are valleys very reminiscent of runoff valleys on the Earth means that the water must have been really much more stable than it is today. It has to have been long-lived and last long enough to flow many times through this and carve these channels. We also see features that look like catastrophic flood channels. Let me draw your attention. Actually, let me back up here. These channels are hundreds of meters to maybe a kilometer wide. This one, where you can, especially from the back of the room, you can see the channel carved by water. Look at the scale bar up there. That's 100 kilometers. This is a channel, what is that, 150 kilometers wide, that was filled with water at one time, water flowing through the whole thing. 150 kilometers is here to Colorado Springs. So this is very reminiscent of something like the Mississippi River in flood stage. That's a lot of water. If you ask the question, why do I think these were carved by water? You know, could it have been carved by the wind? Could it have been carved by lava flowing over the surface? Could it have been carved by liquid CO2? I'm going to resort to what is a very technical geological argument that points toward water having carved these. And this is the most technical I'm going to get, so bear with me on this. These things, we think these things were formed by liquid water because they look like they were formed by liquid water. Did I go too fast on that one? I could do it again if you'd like to. More evidence. This is Gale Crater, where the Curiosity rover is traversing. This was where it aimed. It's somewhere up here right now. And this was a giant, it's a giant impact crater. What is it, maybe 80, 100 kilometers across? And the geological and geochemical evidence points toward this having been an ancient lake. You can see where water flowed out of it over there. This was filled with water at one time. People have been to Crater Lake. Where is that, Oregon? I'm not one of them, apparently. And you see this volcanic crater filled with water. Here is an impact crater that was filled with water. It takes a lot of water. You have to have stable water being stable there. At a smaller scale, this is...
what's the date?
Today's date is, what, November 6th? These rocks date to about 3.5 billion years ago. So if we look at these pictures, this one was about 3.8, 4 billion years. This was about 3.5. This is about 3.5. Younger than this, we don't see many features indicative of water. And that's going to be one of the themes of this series of charts, the fact that something changed. When we look at the landing site the vicinity of the landing site from the the Opportunity rover, the one that just died last summer. They went to this region because they saw geological evidence for a mineral called hematite that forms in the presence of liquid water. These things that are referred to as blueberries, they're about the size of a blueberry, a big blueberry. Actually, I'd call them, this color's been stretched to make it look blue. They're really less red berries, but that doesn't sound as catchy. These things are the hematite that they saw, and this type of feature forms very typically in the Earth in an environment where water is flowing through the rock. It dissolves it in one place and precipitates it out in another place, and you get these things. They're being exposed by erosion. When we look globally, these dots, this is a global map of Mars, these dots show all the locations where minerals have been identified from orbiting remote sensing that require the presence of liquid water to form. They're all on the older surfaces. The whole northern hemisphere is younger stuff and shows very few of these features. Something changed in the stability of water, and we can think about what that might have been. The question that we're talking about tonight, Mars once had liquid water at the surface. It doesn't today. I can spend the rest of the time talking about what happened. We'll talk a little bit about it. But can we get that water back? Can we terraform Mars to bring that water back to the surface? By terraforming, what I mean is doing something to change the environment so that Mars would be warmer, maybe warm enough to allow liquid water, so that the pressure in the atmosphere would be thicker, so that maybe we could get by with breathing gear because we want oxygen, or at least I do. What can we do to raise the temperature and make the planet more Earth-like? The reason this has become a very hot topic is because of this gentleman, Elon Musk. He made his money initially in PayPal, and he decided he wanted to do other things, so he created Tesla in order to make popular electric cars to do good. He created SpaceX, space exploration company, in order to be able to go into space. And he's been one of the most outspoken proponents of the idea of terraforming Mars. And he said you need to live in a dome initially, but over time you could terraform Mars to look like Earth and eventually walk around outside without anything on. I think he's referring to spacesuits. But, you know, with Elon Musk, you can't really tell. I don't think he's referring to a planet-wide nudist colony. But I don't know the answer. We know that he says, so it's a fixer-upper of a planet. We know that he's serious about this idea of terraforming because he created t-shirts. You can go online and buy this t-shirt. I just pulled this image off the web. I had to clean up the image because it just wasn't very good when I pulled it off the web. And he has a slogan, Nuke Mars. He wants to nuke it because if you explode, he says, if you explode nuclear weapons over the polar caps, all the heat will put the CO2 that's present as ice back into the atmosphere, and you put the CO2 in the atmosphere, it's a greenhouse gas, it warms up the planet, you're done. So that's what I want to talk about tonight. Not nuking Mars, but is that feasible? Can we find enough CO2 on the planet and put it back in the atmosphere? Can we do this using current day technology? That's the key. So first, now I am going to get a little technical. How much CO2 would we need? This plot is a model calculation. It shows what the average temperature of the surface would be as you add more CO2 into the atmosphere. You put more CO2 in, the temperature goes up. If you want to get up to the melting point of ice, the freezing point of water, 273 Kelvin, 0 degrees C, you need to add about 1 bar of atmosphere. 1 bar is the atmospheric pressure we have at the surface of the Earth here. So we need as much atmosphere as we have on the Earth today, but CO2. CO2 is a very effective greenhouse gas. We're doing that experiment today. We're adding CO2 into the atmosphere and watching how the Earth climbs up this curve. I actually think that's really amazing, that I would never have thought people were so broad-minded as to do this experiment on the Earth just to find out how Mars would behave when we add CO2 to the atmosphere. What I want to do is ask, do we have enough CO2 on Mars that we can find the equivalent of a bar, and can we put it back into the atmosphere? To put it into perspective, let's see, there are two ways I can put it into perspective. First is to ask, how much CO2 did Mars ever have? And we haven't gotten a clue on that. We don't know how to calculate it. We don't know how to measure it. The closest I can come is to say, well, we know how much CO2 is on the Earth. And it's not just what we have in the atmosphere. It's not just what we're pumping into the atmosphere using burning fossil fuels. It's all the CO2 that's locked up in rocks, in carbon-bearing rocks. It's equivalent to about 60 bars of CO2. Venus, another rocky planet in the inner solar system, all of its CO2 is in its atmosphere. It has about 100 bars. And if Mars had as much CO2 as Earth or Venus on a gram of CO2 per gram of planet basis, and you put it all into the atmosphere, it would be about 20 bars, about 20 times as thick as the Earth's atmosphere. I threw this in there for comparison. If it had as much water as the Earth on a gram per gram, grams of water per gram of planet basis, it would be a layer about 2 kilometers thick. So if Mars had 20 bars, where did it go? The other point of comparison I want you to keep in mind is the current thickness of the Mars atmosphere. It's about 6 millibars. So that's 6 1,000ths, a little over 0.5% of the pressure of the atmosphere on the Earth. So can we find enough CO2 to do this? Where do we look? First, Elon Musk had it right. We're going to look in the polar caps and identify CO2 ice there. We can identify CO2 that is locked up in the ground, attached to the individual dirt grains on a molecule-by-molecule basis. We can look at CO2-bearing minerals, carbonate minerals that are in the surface, and maybe we can even just wait for volcanism to put more gas into the atmosphere. Mars is a complex system, even though it doesn't have an ocean, and I've tried to identify here all the places where CO2 can move around. You can have fresh gas coming out, it can be locked in the deep crust, it can be locked in the polar caps, of course the atmosphere, the thin tenuous upper atmosphere, you can't store much there, but you can look at how much has escaped. So what I'm going to do is go through each of the processes that can remove CO2 and ask how much has it removed. How much is in each of these sinks, each of these reservoirs for CO2, and can we find enough CO2 to assemble an atmosphere of a bar? And I'm going to start with my favorite spacecraft mission, the Maven mission. As Laura said, I'm the principal investigator on Maven. This has been my life for the past 16 years. Maven has been in orbit now for 5 years. It just passed 10,000 orbits. And it was designed to look at the role that might have been played by loss of atmosphere to space. You know, on this, it's this whole upper row. How much gas has been lost? And I am going to get technical here for just a minute. We can determine how much is being lost today and extrapolate that backwards in time. This graph shows the loss rate of oxygen that probably comes from either CO2 or water throughout the Maven mission. This is as a function of time throughout the mission, as inferred from photochemical processes driven by the sun. And we measure it, each dot is an orbit, it looks like it's all over the place and makes no sense, but the Maven orbit precesses, it moves, and we're measuring all sorts of different local times and latitudes. If we organize all of these data by the angular distance from the sun in the atmosphere, it gets a much more consistent pattern. On the day side of the planet, you get high escape rates. Not a surprise, because we're talking about photochemical processes that are driven by sunlight. And the colors represent how much ultraviolet light from the sun is hitting the planet. We measure that. And you can see that the orange and reds, where there's more ultraviolet light, you get greater loss. The greens and blues, where there's less, you get less. This turns out, this tells us how loss occurs, and it lets us extrapolate to determine the integrated loss through time. This is one process. We've looked at many processes. I'm going to show you one more here. This is the ability of the solar wind to strip ions out of the upper atmosphere. A molecule gets hit by an ultraviolet photon, it kicks off an electron, it ionizes, a charged particle can get grabbed by the solar wind. This represents an entire Mars year of data. The arrows show the direction that the atoms are being accelerated, the colors the density, and you can see stuff being dragged down the tail. The sun is way off on the right. You can see stuff escaping in a polar plume. And you can also see stuff coming in and being accelerated into the planet where it can knock stuff out. So we looked at this and we're trying to understand it. That polar plume, to me, was very reminiscent of a mohawk haircut. You can see that, right? Thank you for nodding and humoring me. I appreciate that. We were trying to figure out how best to describe it, and we started with Mr. T. This didn't look quite right. It's not the same shape. Our second attempt to model this was with Alfalfa from the Little Rascals with his little polar plume going out the top of his head. That didn't look quite right. We finally settled on Miley Cyrus. This is exactly what we're seeing at Mars, with this polar plume going over the top of the head and back and very little escape on the side. So if you get nothing out of the talk other than this, I want you to remember that Mars is like Miley Cyrus. But since it's a commutative property, Miley Cyrus is like Mars. I didn't say from Mars. From all of this, we can determine the escape rate, but there's more because the sun has storms that it can erupt tremendous masses of stuff, not just the usual solar wind. And I am going to walk through this. This graph in the middle shows a computer figure of the most intense storm that we've seen on Maven. The sun is this thing at the middle. At the time this storm occurred, Mars was over here. The Earth was over here. We had a spacecraft here that is watching the sun, and it saw this plume erupt on the left side of the sun, and from here the left side is off in that direction toward Mars. On the right, we had observations from Earth, and it saw the same plume erupting off in the right. And from Earth, that plume erupted off in this direction. It's that plume. We saw this. This is the computer-generated figure based on the data. It's a really big event. This event actually hit both Earth and Mars, even though they're on opposite sides of the sun. And we can look and see what the effect is. I'm not going to walk through this, but we had great measurements from Maven. We saw a giant flare when it began. We saw an increase in all the particles that get emanated from the sun. And we can ask, what was the effect of all of these particles? The first thing is it triggered Aurora on Mars. And this is a before and during shot of Mars at a wavelength in the ultraviolet where we see Aurora. In this before, it was September 9th, 2017. You can't see anything. This is just noise. You can't even see where the edge of the planet is. At its peak, the planet lit up like a light bulb. And you can see it on the edge of the planet. The whole planet is brighter. Global aurora. Here in Boulder, we have a chance every now and then of seeing an aurora, but they concentrate in the polar regions because of the global magnetic field. Mars, without a magnetic field, it hits the whole planet and lights it up. We can use this to estimate how much gas has been lost, and in fact, the loss rate of atmosphere from the planet goes up by 10 times during this event. And early in history, these events were much more common, so this may have been the most important mechanism by which the atmosphere evolved. We have one more indicator, and that is isotope ratios. And I know there are at least a few people that know what I'm talking about. atoms like nitrogen here come in different masses. Normal nitrogen has a mass of 14, heavy nitrogen a mass of 15. When the stuff gets stripped away, the lighter stuff is removed more easily. It leaves the stuff that's left behind enriched in the heavier stuff. And we see that when we look at hydrogen, nitrogen, argon, carbon, oxygen. All of them show the same pattern of enrichment of the heavier version of each atom. And that tells us that escape to space has been a major process. We can use this to estimate how much gas has been lost through time, and it's in the range of 1 or 2 bars. Remember, we're looking to find 1 or 2 bars that might have warmed up the planet, maybe out of perhaps 20 that the planet might have had. So here's 1 or 2 right there. The main conclusion we draw from this, and the main conclusion coming out of the Maven mission, is that loss of the atmosphere to space, stripping of the gas by the sun and the solar wind, has been a major process in evolution of the atmosphere. And I wrote a major process only to not give it away, because what it used to say was the dominant process. But it's certainly one of the major processes by which the atmosphere evolved. So loss to space is the biggest sink for CO2. What about the other sinks? I went through that in some detail. I'm going to just mention these in passing because we want to add up how much gas might have been lost in each one. Early in history, Mars formed by being bombarded by giant asteroids, planetesimals that helped form the planet. If there was an atmosphere, each one would also splash off atmospheric gas. We can add up how much gas has been removed, and it's probably in the range of 500 to 1,000 millibars, so half a bar to a bar, another major process by which the atmosphere evolved. I mentioned carbon-bearing minerals. 20 years ago, the major focus in Mars research was to look for all these carbonates on Mars as the sink for CO2. We did finally find some. We've seen it in the global dust. It has maybe 1% or a couple of percent of carbonates. We found it in the Neely-Fosse region, and man, for the life of me, all of a sudden I can't remember where that is. I think it's up here somewhere. And in that one region, carbonate minerals have been exposed by weathering of rock at the surface, and we think it has the equivalent of about 12 millibars of CO2. You can push that up depending on what assumptions you make, maybe as high as 150, but going above 12 you have to make increasingly unrealistic assumptions. So I like the number 12. And then they've discovered deep carbonates that are exposed by impacts where it digs out a crater or on the side of canyon walls. And it's hard to know what you're seeing because you don't know if it's a local thing or a global thing, and you're just seeing it in places. So it could be as little as 10 millibars or as high as a bar. This is another important sink. So that's about 3 sinks. I mentioned CO2 in the polar caps. This has been detected using radar. This is a radargram looking through the ice in the South Polar Cap, and these dark regions are where it's CO2 ice. The amount of CO2 ice, you can just map out the volume, and it's equivalent to 6 millibars. So the same amount of gas as is in the atmosphere. So right away you know Elon Musk is wrong. If you nuke the polar caps, you only get 6 millibars out. You double the pressure in the atmosphere. That ain't a lot. I'm going to mention these two just because they come up on the table. There's something called water CO2 clathrate hydrate. It looks a lot like water ice, but with a cage structure and a CO2 molecule rattling around in the middle. There could be 0 of that. That's my favorite number, but there could be as much as 30 millibars locked up. This would be locked up in the polar ice. And then I mentioned CO2 attached to the individual dirt grains. And depending on what the composition is, I think there could be as much as a few tens of millibars of CO2. So let's add it all up. I went through that really quickly because I wanted to get to this table. How much CO2 can we account for that has been removed from the atmosphere? I've listed each of the processes that we've talked about. Impact ejection, stripping by the solar wind, polar ice, just to keep reading, carbonates, adsorbed gas, deep carbonates. You add it all up, and you have between 1 and 3 bars, 1.5 and 3 bars of CO2. So there's enough CO2 on Mars that were it all in the atmosphere, it would warm the planet. The question is, by the way, this plus is here because we don't know really how much there could have been. All those solar storms early in history, this could be many times larger. There's a lot of CO2. Can we put any of this back into the atmosphere? So the question I'm going to change to here is, can the CO2 be mobilized and put back into the atmosphere? That's what we need to do if we want to modify the atmosphere, terraform the atmosphere. We're going to start with the easy ones. Polar ice. I already said there's 6 millibars. You nuke the poles, you double the size of the atmosphere. The polar regolith and clathrate. This is that funny CO2 water ice mixture. You put that back in. It could be 0. It could be as much as maybe 30 millibars. I'll give it 30 millibars. That's fine. Let's talk now about the ones that are harder. Impact ejection to space. Can you get that back? I see a couple of people nodding no. Very astute. It's very hard to imagine. Once it's gone, it's gone. So let's cross that one off. What about solar wind stripping of the atmosphere to space? By the way, just because I'm going to plug Maven here, you see that's the biggest number on here. 1 to 2 bars, 1,000 to 2,000 millibars. That's the biggest sink. But again, once the CO2 is gone, it's gone. It ain't coming back. So we can cross that one off. Let's get to the more interesting one. What about these deep crustal carbonates? These are carbon-bearing minerals that reside maybe 5 kilometers below the surface. If it's a global layer, it might hold as much as a bar. All you have to do to release that CO2 is heat it up to about 300 or 400 degrees C. So what you need to do, if you want to get that back into the atmosphere, is strip mine the planet globally to a depth of about 5 kilometers. I'm going to cross that one off. Near surface carbonates. You know, maybe there's a dozen millibars, maybe twice as much. Maybe there's places we haven't identified that have it. Again, if you want to release that, you've got to heat it up to 300 or 400 degrees C. Even though the bulk of it, the bulk of the carbonates we know about near the surface is in one place, it's still an area 50 or 100 kilometers wide. So you're talking about strip mining an area the size of Rhode Island or bigger. I'm going to cross that one off. Adsorbed gas, by the way, this is the one that Elon really likes because he says there could be as much as 10 times this amount, and all you have to do is apply a little heat and it'll start coming out and it'll run away and put a little out, it'll heat it up, more out. Doesn't work that way. There's probably only a few tens of millibars, and I think if you start to heat up the planet you can get a few millibars out. So I'm going to cross that one off. What are we left with? It's the ones that are easy, and you can get them back just by nuking the polar caps, a few tens of millibars. Remember, we need a bar, 1,000 millibars or so, to raise it up. So can Mars be terraformed? And remember, we're talking about, can it be terraformed using today's technology? I hope everybody knows the answer. It's really not going to happen. That's the bottom line story. But it gets more interesting because suppose we did want to terraform Mars. Suppose we weren't limited to today's technology. One possibility is we could create, design, and manufacture high-efficiency greenhouse gas. Those of you who are in the room who are older will remember Freon from refrigerators. That's a high-efficiency greenhouse gas, which is why we no longer make it. You could design other chlorofluorocarbons that have chlorine, that have fluorine, that have carbon, that would be very efficient, and start putting them into the atmosphere, and they could warm up the planet. I'm not sure that's a very nice environment to be in, but the real problem is it sort of requires a manufacturing capability beyond what we can do on Mars today. Remember, You know, we're not talking about a manufacturing station the size of this table that we could put on a spacecraft and take to Mars. We're talking about a manufacturing capability the size of the IBM plant times 100. That's a little bit beyond today's technology, but I'll give it the benefit of the doubt and leave it as an open question far into the future. However, there's a part of me that thinks, you know, as long as we're going off into the realm of technology that we don't know how to do, there's an easier way, and that is, let's just take all the CO2 from Venus and move it to Mars, and we get 2 terraformed planets. So if you remember Elon Musk's T-shirt, Nuke Mars was a slogan. This is ours. Keep Mars red. Yeah. It ain't changing. That said, there is the possibility of human missions to Mars. Elon Musk and SpaceX have a vision of creating cities on Mars. See, I'm not anti-Elon Musk. I just think this idea of terraforming makes no sense. But he's done truly amazing things with rockets. He's building his Starship, as he calls it, that can go to Mars and land on the surface. And he wants to create cities on Mars. You notice that his cities are all in domes. The United Arab Emirates, a couple of years ago, announced plans to create a city on Mars by 2117. They're very forward-looking. They want to have an impact on the world. This is positive. I'm not going to say anything snotty about it. But they envision a world that has domes on it as well, creating a city. I want to address a different aspect of terraforming for a minute, and that is why we want to do it. This is from Calvin and Hobbes' cartoon. So long, Mom. Hobbes and I are going to Mars to live. Earth is too polluted. Elon Musk talks about Mars as an Earth 2.0, as our backup planet in case we screw up the Earth so badly that we need another place to go to get away. This is a dangerous idea because it suggests that the Earth is expendable, that we don't have to take care of it because we can move on. Ain't going to happen because Mars is not Earth 2.0. It's not possible to terraform the planet, and it's always going to be a really harsh environment. The way I think of it, no matter what we do to the Earth's environment is always going to be closer to what we have today than Mars is. It's always going to be easier to fix Earth than to terraform Mars. So I think this idea of having Mars as a backup planet is a really dangerous one. But I want to end on a positive note, and that is, where are we in exploring Mars? Remember at the very beginning I said that the overarching question for Mars from a scientific perspective is, did it ever have life? What we've seen is that Mars meets all of the requirements we would place on an environment in order to support life or to have had an origin of life. Access to all of the elements needed to create life, things that you can combine together in lots of different ways to create complex chemicals that do interesting things. A source of energy that can drive metabolism. This energy on Earth, most life, is driven by sunlight. Not all life. There's some life, a very tiny amount, that gets its energy from chemical reactions between water and rock. So if you have rock and you have liquid water, you have a source of energy. And we've seen the geological evidence for liquid water. This is just up here as eye candy. This is the Allen Hills meteorite that led to an announcement a couple of decades ago about possibly finding fossilized organisms inside of it. I don't think very many people believe that today, but this rock is a plausible rock to have had life because it had liquid water flowing through the rock, and it dates back to the earliest history of Mars. We've seen the geological evidence for water and how it's changed through time from the ancient history with valley networks. And I haven't talked about this process, but very significant, substantial degradation that is consistent with liquid water. Catastrophic flooding in the Middle History, including channels that look like they arose out of nowhere, with water perhaps coming from under the surface, and then recent geological evidence for water. We have the evidence for liquid water. We know it was there. I've shown some of it today, not all of it. So it's not a stupid question to imagine that there could be, well, that wouldn't be a question. It's not a stupid question to ask if there could be life on Mars. And that's what we're doing. The best way to find out if there's evidence for life on Mars is going to be to go to the planet, collect samples from a known location that might have had liquid water, that might have had life, and bring them back to Earth. And that's the project that we've embarked on now. We, in this case the United States, we're launching a rover next year, very cleverly called the Mars 2020 rover. They're about to hold a contest to come up with a better name. I hope the name isn't the Mars 2022 rover. The last one was delayed 2 years. It's the size of this table. It's the same size as the Curiosity rover. It's going to go to a place where we know there was liquid water. It's going to collect rocks and leave them to be picked up. They're going to be picked up by a later spacecraft and launched back to Earth, where they're going to land in the desert in Utah, because of course Utah is expendable just in case. And we're going to look in the rocks for any evidence for life. In addition, we do have the technical capability to do human missions to Mars. This is an example of what one might look like that comes from the Lockheed Martin Corporation down the other side of Denver. This is a spacecraft we could assemble in Earth orbit and send to Mars. If you're familiar with the Orion spacecraft concept, this is an Orion capsule here, the service module, a habitat, and because just in case, a duplicate of everything, because you never know what's going to happen. In addition, Elon Musk is trying to get to Mars. I second that motion. Oh, come on, how about a chuckle at that one? Thank you. He's going to do it with his Starship. He's claiming that he might be able to do it in 2024. I don't believe that, but I do believe he'll be able to do it. And I do believe he will have that capability. I think it's a race. Who's going to get there first, NASA or Elon Musk? And just recently, Jeff Bezos and his Blue Origins company has jumped into the race. They're part of it as well. The bottom line is we could send people to explore Mars, and I think this would be an incredibly exciting thing to do. We're learning about planets other than the Earth, planets that might be able to sustain life, and we're asking the question of, could there be life on Mars? If there is, or if there isn't, it's going to tell us a lot about the distribution of life in the universe. And with the discovery of planets around other stars, you know, in my lifetime, we've gone from 0 known planets around other stars to something like 4,000 today. And the discoverers of the first known planet around another star just won the Nobel Prize for their work. It's a major effort. It's a major discovery. What we learn in our solar system is going to tell us a lot about how widespread life might be. And this question of could there be life elsewhere in the universe is one that I think is of tremendous interest to us as individuals, as a society, and I can say in all honesty, we actually have the chance of answering that question, at least about life on Mars, within my lifetime. And there are people in this room, some of whom I see in the back row sound asleep, who have the chance to become the first astronauts to go to Mars. So on that note, thank you for coming out, and let's keep Mars red. Thank you. We have time for questions or rebuttals. Yes?
My question is about making Mars blue and green. Is there any evidence of like asteroids that contain CO2?
There is comets more than asteroids, and you can imagine that if we bring a comet that has a lot of CO2 and smash it into Mars, we get all that CO2 plus the water from it. So how many comets would it take? If you add up the total mass of an atmosphere needed to get it up to 1 bar equivalent, you would need 1 million comets that are 1 kilometer across that were made entirely of carbon dioxide. So if you can crash, first of all, if you can find them, but then if you could crash 1 million of them into the surface without completely destroying the planet, more power to you. Yes?
Do we have all the nitrogen in the solar system, and why is that?
We don't. We have nitrogen. Venus has a similar amount of nitrogen. Mars has a dearth of nitrogen. Very, very little. We don't know how much might be locked up in nitrates in the crust. We do know that there's some. It's been detected from the Curiosity rover. We know that there's nitrogen in the atmosphere, and that potentially is one of the limiting factors in how much life there could be, because nitrogen is pretty important for life on Earth. Yes?
Follow up to that one then. In early Martian history, what sort of filler gases were prominent then? Do we have any indication of other than CO2?
That's a really tough one to answer, because we're looking at all these clues and they're secondary clues. They're not good indicators of what the atmosphere was like. So we think there was more CO2. We think there was more water. There's evidence that there was some more nitrogen, more argon. Exactly how much, I don't know. One of the games we're trying to play is taking what we see today and integrating backwards in time to guess at how much of each gas there might have been early on, what the atmosphere might have looked like, and where did that gas come from? We don't understand where the gases from planetary atmospheres come from. So it's a very difficult game to play. I'm trying to keep the Maven team from doing that right now, because it's easy to get lost in that and lose sight of what we can actually measure. Yes?
Why doesn't Mars have a magnetic field? And did it ever have one? Or do we think that it one time?
We've been able to measure, we sent a magnetometer, we've been able to measure whether there's a magnetic field. We know it does not have a global field the way the Earth does, and we can understand that. The Earth's magnetic field is generated by motions of the molten outer core that's made of iron and nickel. You take an electrically conducting medium and move it around, and you can generate a magnetic field. Mars is smaller than the Earth. We think that its core would have cooled off more quickly. It probably has frozen out and therefore doesn't drive the motions. We know that Mars did have a magnetic field because we measure remnant crustal magnetism in places, and that can only form as, for example, lava cools off in the presence of a global magnetic field. The timing of that, based on where it occurs and where it doesn't, suggests that Mars stopped having a magnetic field about 4.1 billion years ago. Yes?
So if you put people on Mars, are you worried that contamination from everything we have will start to spread around and then corrupt maybe measurements of life that could have been on Mars?
We've had, since the beginning of the space program, we've had what's called a planetary protection program in order to keep us from contaminating Mars and other places that might have life. And when we send humans to Mars, there's a real risk we're going to muck it up. It's really hard to sterilize people. I mean, not in the sense of not in the sense of snip, snip, but you can't put them in an autoclave. Well, you can, but that would be counterproductive. You can't kill off all the organisms. We are going to contaminate Mars when we send people. I think NASA is just now starting to come to grips with that and thinking about what sorts of procedures, what sorts of requirements do we want to put into place to keep the contamination to a minimum, or to keep it isolated to some locations and not others. I don't have the answer. I think people are struggling to find the answers, to find a balance between we can't do anything for risk of contaminating versus we want to go there, to hell with the contamination, whatever happens, happens. Somewhere in between is the right answer. Yes?
Why not go to Venus then?
It's really hot.
It'll sterilize any contamination.
Yeah, but you put a spacecraft down on the surface of Venus, and if you're lucky, it will survive for 4 hours before the heat soaks in and fries it. If you think Mars is a harsh environment, Venus is a really harsh environment. Temperatures, what is it, 750 Kelvin?
Yeah.
So that's like 1,000.
And boiling gas.
500 degrees C. Sulfuric acid, yeah, you got that right. No water to speak of. Very little. If you took all the water vapor in the atmosphere in the clouds and condensed it out, it would be a layer, negligible thickness. And by the way, did we mention it's sulfuric acid?
Yeah.
So it's a really tough environment. You could probably create balloons that ride up at 60 kilometers where it's a very pleasant 1 bar atmosphere and room temperature. You just have to make sure you don't pop it and fall down to the surface. I don't think human missions to Venus are on anybody's radar screen right now.
There'd be lots of solar energy.
There's lots of solar energy in Phoenix, but I don't go there in the summer very often either. For the same reason. Fran.
Okay.
Yeah, we're not going to go to the outer planets.
You've shown that you can't terraform Mars, number one. Number two, you've shown that the water on Mars was, any standing water was there, say, 3 billion years ago. That if you look at Earth, the most sophisticated life form 3 billion years ago is slime mold. So the best you could find on Mars is slime mold, fossilized slime mold, 3 billion years old.
You say that as if it's a bad thing.
They would be fascinating. It'd be fascinating to go look at it and compare it with what the slime mold on Earth, fossilized slime mold on Earth. But why send the humans? It's completely and utterly pointless. You're going to contaminate Mars. Why not just send the robots to go and find out what this slime mold that could be fossilized on Mars?
Fran and I have been having this argument for 20 years, and we're jointly teaching a graduate seminar this semester on human missions to the Moon and Mars, and we have this argument. I'm looking at the 2 students behind you. Every class? They're nodding yes. And ultimately it comes down to what kind of explorers do we want to be? Do we want to send robots, which are wonderful things? I hope you get the idea. I like robotic spacecraft. Or do we want to actually... I'm sorry, are we talking one-way trips now? Or do we want to actually extend our presence as a real presence out into the solar system? And it's not an argument of which is better. And that's the way Fran tries to cast it every time we have this argument. You know, which is better to climb Mount Everest, a human or a robot?
Money, come on, taxpayers. We don't taxpayers pay for this.
And I remember being 6 years old and sitting in front of the TV. This will tell you how old I am. Sitting in front of the TV watching the countdowns for the first Mercury astronauts. And I think that's why I'm in this business today, because it really is exciting. And I hate to think that the world we live in would have changed so that we're no longer sending people into space to do useful and valuable things. That's my best argument.
Yeah, I think humans have a drive to explore, and you're probably not going to stop that.
Sure, let the rich people go pay for it.
Anybody other than Fran have a comment? Yes, sir.
If we find life on Mars, what do you think the chances are that it would be independent of Earth, or
good question.
That's a fundamental question.
Transported back and forth by asteroids to get back to...
What he's alluding to is the fact that impacts of asteroids, which happen all the time on planets, can knock rocks into space. And a rock knocked off of Mars can find its way to the Earth. I didn't bring it tonight, but I've got a couple of meteorites back in my office that came from Mars and found their way to the Earth. The Allen Hills meteorite that was picked up in Antarctica is a Martian rock that found its way to Earth. The conditions under which these are ejected can be gentle enough. It's hard to imagine an impact that sends a rock into space, but it can be gentle enough that if there are organisms living inside the rock, they might get off the planet without being killed. And you have the ability to transfer life between Earth and Mars. We don't know whether that happened. It's a hypothetical. If we find life on Mars, that's going to be the second question. The first is it a contaminant we brought with us? But the second is, does it represent an independent origin of life, or does it share an origin with life on Earth? That's a fundamental question, and it affects how we interpret it in terms of life in the universe. I really want to see that answer, but until we find life, we can't even, there's nothing you can do about it. Last question. Yes, sir.
With regards to the Martian dynamo sort of winding down, does that suggest, is it just a scale thing based on the size of the planets and the cores, or is it sort of suggestion that Mars had a magnetosphere earlier, or was formed earlier?
We don't know enough about the Martian core to really be able to answer that. The last time I read some of the technical papers about the Martian core, one of the free parameters in running these models is how much oxygen or silicon got incorporated into the core as a contaminant. And oxygen, for example, will cause it to either cool off more quickly or less quickly, depending on how much. And if you tell me what date the core froze out, I can tell you how much oxygen you need to have had so that it would freeze out on that date. That doesn't mean that that's what happened, but it means we don't know enough to really be able to answer that question. There are too many unknowns, and the core is even harder to get out than any subsurface water. Thank you all for coming out tonight. Really appreciate it, especially in this weather. Thank you.